So in a square, all four sides are equal, and each one of the internal angles is 90 degrees. So all these four angles are 90 degrees. And if I call the side S, then the perimeter, which is the sum of the lengths of the four sides, is just 4S. And the area of the square is just side times side, or S square. Another important dimension is the diagonal. So that's the diagonal. And if you look at this, the triangle that I formed here, so this is 90 degrees here. These two sides are equal, and so these two angles have to be equal, and each has to be 45 because this is 90 here. So this is a right isosceles triangle. So if the sides are SS, then the diagonal is side times root 2. So the diagonal of a square is given by side root 2. So it's an important property. Now, if we look at rectangles, again, each of the four internal angles are all 90 degrees. So these are all 90. And if you call one of the lengths L, the other is width, then the perimeter, which is really the length of the outside dimensions of this four-sided figure, is just twice the length plus twice the width, because these two are just same as length, and then width and width. And the area is given by length times width. Now, in the case of a rectangle, to find the diagonal, you create this right triangle here, and the two sides are length and width. So if the diagonal is D, we can apply the Pythagorean theorem. D squared is equal to L squared plus W squared, which means the diagonal is square root of L squared plus W squared. So you can use that relationship, or just apply the Pythagorean theorem to the given dimensions. Now, the next concept is the area of a triangle. And I'm going to draw a general triangle here. And the way you can think about this is that if you were to surround it by a rectangle, actually my triangle is a little bit at an angle, so then let's call this the base. And if we draw a perpendicular here, so a line that's perpendicular to the base from this corner, then this triangle, which is this entire this region, surrounded by this rectangle. So if I look at the area of this portion, this would be half of this rectangle. And then if I look at this shaded part, would be half of this other rectangle, which means that the area of the triangle would be the area of this rectangle that surrounds it, and the two dimensions are base and height. So you find the area of the rectangle that surrounds it and divide by 2. And that's where the half base times height comes from. Now, when you have a triangle, as far as the height, you always look at the perpendicular distance to the base from the opposite side. So if it's something like this, then this would be your perpendicular distance. This would be the height. And then that length would be the base. And you can choose any side to be the base or the height. It's completely arbitrary. Like here, if this is the base, then the height would have to be this. But if you chose this side as the base, you would have to go from this end and draw a perpendicular, and that would be the height. So it doesn't really matter which side you choose as base. Now, in case of a right triangle, because these two are perpendicular to each other, you can choose this as the base, this is the height, if you're looking from this direction, or you can call this the base, and this is the height. So in this case, you don't have to find the altitude, whereas something like this, you may have to figure out a way to find that height. And if it's a problem on the GRE, there would be a way to figure that part out. Okay, so the next concept is circles. And a circle is really a set of points that's equidistant from a given point, which is called the center. So So basically, it's a collection of these points that are the same distance from the center. And this distance is called radius. And if you draw a line from one end of the circle to the other passing through the center, the length of that line segment, it's called the diameter. And the key relationship is regarding circumference. So circumference really just refers to the outside perimeter of this circle, and it's given by pi times diameter, or 2 pi r. So essentially, diameter is twice the radius, but generally we write it as 2 pi r. So that's one of the key relationships. Now, the area of a circle, so the formula is pi r square. And what I'm going to do is to show you a quick proof. There's a lot of confusion about the formula for the area versus the circumference. A good way to distinguish them is circumference is a length. It would be in inches, feet, meter, whereas area is covered, square feet, square inches, square meter. And that's why you have this r square here. So I'm going to just give you a quick proof. So let's say you have this circle, and I'm going to divide this into 100 slices. Lots of 100 slices, and I'm going to call this B, this length here. Now, if the slices are really small, then it's not the best. Okay. Then this curved part is almost the same as that. Of course, if it's really large, I mean, for example, here, then this curved part and this piece is different. But as you make these slices smaller and smaller, they're almost the same. So we're going to use this approximation. So each one of these slices is a triangle. And the height here is almost the same as the radius. So it's really, this is of course an expanded view, but as these slices get smaller, that height is about the same as the radius. So the area of a triangle, each one of these slices is like a triangle. So base times radius over 2. And I said there are 100 slices. So the area of this circle would be 100 times b times r over 2, because we have 100 of these slices. Now, if you look at all these pieces are b, and if I know that there are 100 slices, then 100b is the same as the circumference, because I decided to cut into 100 pieces, and each one is b. So it means that this is the circumference, and we wrote the circumference as 2 pi r. And if I substitute that here, simplify this, I get pi r squared. So this is a rough sort of a proof to show you that the area is pi r squared, so that might be easier for you to remember. The other concept has to do with arc length and area of a sector. And let's look at a general case. So we have, say, a circle center here, and I'm drawing the sector where this angle is 40 degrees. And usually to describe an arc, we always use 3 letters, because if you just use arc AC, it's not clear whether we're talking about this arc here or we're talking about this major arc. So by using 3 letters and saying arc ABC, it's clear that we're referring to this minor arc here. And let's call the radius is 18. So the way to find the length, so the first part is the arc length, or length of this curved portion. You first find this angle 40 degrees as a fraction of 360, because 360 is referring to that entire angle. And that's 1/9. And then the arc length would just be 1/9 of the circumference of that circle. So here, the radius is 18, and we can simplify this. This is 4 pi. Typically, often the answers would be left in pi, unless they expect you to approximate. In that case, you would be using pi is equal to, I would say 3.1 is usually enough, but if you want to be really certain, 3.14 is more than sufficient for the GRE. Now, same thing for the area. The approach is, once you find that piece or this fraction that this arc is of the entire angle, then the area is just 1/9 of pi r square, where here the radius is 18. So it's pi times 18 times 18 over 9. 9 goes into 18 twice, so this is 36 pi. So that's the general approach for computing the area and the length of these arcs. Okay. The other important relationships come up with circles and squares when they are inscribed or they circumscribe. So let's look at a circle, and let's say we have a square that circumscribes it, meaning it goes all around it. And here, this is the radius. And you can think of this as this is the diameter. So the relationship is that the side of the square, if we call that S, is equal to diameter equal to twice the radius. So that's the key relationship. And the other is if you have a square inscribed in a circle. So here the relationship, this is a little bit tricky, is that the diameter, or D, is equal to the diagonal of the square. So if the side is S, and we saw this earlier, the diagonal is S root 2. So here D, or 2R, twice the radius, where R is the radius, is equal to the side times root 2, or the diagonal. So this D is the diameter, not the diagonal. So those are the two key relationships. And if it happens to be a rectangle, so something like that, then again it's the diagonal of the rectangle, which is the same as the diameter. So here D square, which is also the diameter, is L square plus W square. So you might see variations of that idea. So the next concept has to do with cubes. So if we look at a general cube, so a cube has 6 faces. So the way you can think about this is you have 4 faces on the side, that, and then 2 on the top. So it has 6 faces. Each face is a square. And also it has 8 corners. So you can think of the bottom 4 and then top 4. So 8 corners. And then the number of edges referring to these. So in the bottom you have 4 of these, and then 4 on the top, 8, and then 4 standing. So there are 12 edges. And each face is a square, so if the length of the side is L, then the area of one face is L square. And the surface area, which is the entire outside area of this cube, would be 6L square. And then the volume is just L cube, or length time length time length. So those are the 2 important relationships. Now, there's also, you need to know the longest diagonal of a cube. So I'll draw this out. So let's say you have a general cube. And the question is, what's the length of the longest diagonal? Now, each side is L. So this is L, this is L. And the longest diagonal is if you go from this corner to this corner and you connect those 2 points. And to find that length, and I'm going to call that D, you draw this floor diagonal and you create this right triangle in that corner. See, this would be this diagonal is the hypotenuse of this right triangle. Now, this is not any of the special triangles. So first we need to find out, how do we find the length of this floor diagonal? So think about looking at it from the top. So it would basically be just the floor of this cube. And this is L, this is L. And the length, that dimension that I drew here, would be the diagonal of that square. And we know that if we have a square, the diagonal here is L root 2. So this length is L root 2. Now, if I were to just redraw this right triangle, this is the diagonal, L root 2 is the base here, and L is the other side. So we can apply the Pythagorean theorem. D square is equal to L square plus L root 2 square, which becomes L square plus 2L square, because here you're going to do root 2 times L times L. And this becomes 3L square, which means D is equal to square root of 3L square, which is L root 3. So the diagonal of a cube is its side times root 3. And for a rough approximation, for example, let's say I have a room that's 10 feet by 10 feet by 10 feet. Then the longest diagonal would be 10 feet times root 3, and root 3 is about 1.7. So the longest diagonal would be about 17 feet. So that sort of visually makes sense. The next is the general concept about rectangular solids. So you'll see the term rectangular solids. So here all faces are perpendicular to each other, so almost like a shoebox. So it looks something like that. So again, this also has the same number of faces and corners and edges as a cube. So here the surface area, so let's call the dimensions length, width, and height. And it's really arbitrary which sides are called length, width, and height. And the surface area, this face is a rectangle which has a dimensions of length L and H, would be L times H, and we have an opposite face that has the same dimensions, so 2LH. And then this face is H times W, and we have another one here, so 2HW. And then we have the bottom one, which is LW, and then we have top one, so 2LW. So you really just form these three pairs with these three different dimensions. That's one way to memorize this. And the volume is just the length times width times height. Now, also, we can apply the same approach as we did for the cube to find the longest diagonal of a rectangular solid. And I'll apply that same approach here. So the question is, if you're given any rectangular solid, this is L, this is W, this is H, what's the length of the longest diagonal? So going from this corner to that. So again, we have to find this floor diagonal. And the floor diagonal is the diagonal of this rectangle, where one side is L, the other is W. This would be, if I apply the Pythagorean theorem, let me call this X. This would be X squared is equal to L squared plus W squared. And I'm going to leave it like this. I mean, don't need to do the square root yet. And then if we look at this right triangle here, the diagonal is D, which is also the hypotenuse, is equal to H squared plus X squared, because X refers to this, and the length of this base. And we know that X squared is L squared plus H squared, so I can replace that. So D squared becomes H squared plus L squared plus W squared. And generally we write it length, width, and height. Again, the notation is arbitrary, which means that the diagonal is just the square root of that. So that's the general relationship between the diagonal of a rectangular solid and its three dimensions. Okay. The next concept has to do with the cylinders, and you need to know how to compute the surface area and the volume. So cylinders you can think of as two, and on the GRE you'll see the term right circular cylinder. What that means is, I should write that down, right circular cylinder. The right means that this side, this is perpendicular here. So if you were to draw a line like this, that's a 90 degrees, meaning it's not a leaning cylinder like that. You will not see that. So here the dimensions are height, the height of the cylinder, and then you have the radius. So the area of the top and bottom, so you have two circular areas, that's 2 pi r squared. And then the next is, how do we compute this curved part? So you can visualize this, cutting the cylinder here and then opening this out. Now what you're going to find is you end up with this kind of a rectangle where this dimension is the same as the height. The key is, how do we relate this dimension to the original cylinder? So when you cut this and you open it up, This part is what opens up, and that's the same as the circumference. So this is 2 pi r. So the area, or what's called the lateral surface area of the cylinder, is just 2 pi rh, area of that side face. So its total surface area would be 2 pi r square plus 2 pi rh. So on the GRE, they're very careful. They will describe whether they're looking for total surface area or lateral surface area. And then finally, the volume for rectangular, for a right circular cylinder, is a good way to remember this area of the circle, which is the base, times the height. So it's just pi r square h. So that summarizes the key ideas about the cylinder.